Our first session with short presentations today will be started by Antoniette Grima about the evolution of continental topography at subduction zones. Antoniette, feel free to share your screen and unmute yourself, and then we can get started. We can see your screen, but we can't hear you yet.
Can you hear me now?
Yes, we can.
Okay, perfect. Right. So, so we know that subduction zones are extremely variable, right? And some of this variability can also be seen in the style of subduction. So sometimes we have slabs that dip and deflect at very shallow depths under the overriding plate, and sometimes we have slabs that sink at very steep angles into the mantle. And this very cool, and this, oh, cool. And this is very nicely illustrated by the South American margin, where we have examples of both flat slab segments and steeply dipping slabs along the same trench. And if we look at this topography map, we can see that the style of subduction has a first order effect on the surface. And we can see difference in topography, but also difference in the width of this band of deformation that we can see along the trench. And this variability is not something that only happens in space, but it can also happen in time, as exemplified by the northwestern margin of the United States, where we have this leftover uplift of the Rockies and the Colorado Plateau due to an extinct flat slab episode that occurred during the Laramide orogeny. So we're talking around 65 or so million years ago. Now, subduction zones are even more complicated because apart from this variability, they also most of the time involve continental overriding plates, as we can see in our two examples over here. Now, the continent is complex, as we know from both geochemistry, geophysics, and also rock physics. And we know that the continent is very heterogeneous in terms of its density, its strength, and its viscosity. And this variability can be seen very nicely in this map of S-wave velocities by Brisson and co-authors from 2021. And if we look at the North American continent, for instance, we can see the sharp gradient in S-wave velocities as we transition to the older and colder parts of the continental lithosphere. Now, we know from previous work that having a continent at the trench is extremely important because it helps to stabilize the plates at the surface. And this in turn encourages single-sided subduction, which is what we see on Earth. Furthermore, the continent also encourages slabs to have a steeper initial subduction angle. And this then encourages slabs to penetrate into the lower mantle. But the question is, how does this heterogeneity that we've just been talking about affect the evolution of slab morphologies in the mantle? How does it shape the subduction style? And does it have any influence at all on the overriding plate topography? So to answer this question, we look at the 2D numerical model in aspect using a pre-surface and adaptive mesh refinement. And this allows us to capture at a very high resolution the small scale deformations and deflections that are occurring at the surface of our model. And in our model, we have a viscosity jump at 660 kilometers depth, and at the surface, both our continental overriding plate and our subducting plate are free to move, so they're detached from the sides. And we can see that as the model evolves, we have fast slab sinking speeds in the upper mantle, slab anchoring, and then slab roll back towards the end of our model. But what is really interesting is what's happening in this zone of our model. So let's zoom in that a little bit and try to figure out what's going on. So what I'm showing you here on the left is the topography, the viscosity, and the strain rate of an extremely boring continental overriding plate. So there's no heterogeneity in here, and the continent is the same throughout. On the right, I am showing you the same model, but this time around we've introduced some heterogeneity in the form of this high viscosity continental keel. And we can see that although the slab morphology looks very similar, the strain rate, the viscosity, and as a result, I'm not sure if you can see it, but as a result, the topography is also very different. But this is just a snapshot in time, right? So how does the topography then evolve as the model evolves? And we can see that in the slide over here. So at the top, we have the topography. So on the y-axis, we have the time, the x-axis, we have distance, and in blue and white is everything that is below 0 kilometers, and in green and brown is everything that is above 0 kilometers for a model that has no heterogeneity implemented in it at all. And at the bottom, we can see the slab evolution in the upper mantle during the anchoring phase and in the lower mantle. And what you can see is that there is no focused deformation in our continental overriding plate. What we can see instead is this sort of gentle tilting of the entire continent towards the trench. And this is more pronounced towards the end of the model as well. If we look at the trench retreat, we can see that there is an increase in the trench retreat rates at the beginning of our model. And this decreases and becomes more stable as the model gets into the anchoring and lower mantle phases. Now, what if we introduce some heterogeneity? Well, the first thing that you can immediately notice is that the topography looks very different now. We have a well-defined and well-constrained foreland region. And within that, we have some variation in topography. So at the beginning of the model, we have the formation of an incipient foreland basin. And we can see that this time around, we have these topographic highs, which were missing in the previous model. If we look at the trench retreat rates, we also see that there's quite an increase at the start of our model. During the anchoring phase, we can notice that the foreland basin here has grown both wider and deeper. And the trench retreat rates are also decreasing in response to this anchoring period in the slab. And then we can see that towards the end, we have these 2 pulses of extension in the foreland region, and our foreland basin becomes even deeper. And the trench retreat rates remain constant throughout. So if we compare our trench retreat rate for our heterogeneous continent with our homogeneous one, we can see that at the beginning, the trench retreat rates are very similar, but as the model evolves, we can see that the model with the heterogeneity has a much higher trench retreat rate compared to the homogeneous one. Now, what if we were to increase the spatial extent of this heterogeneity in our overriding plate? Would the topography look any different? And the answer is yes. So what we can see over here is that the foreland region is involves a much bigger area. And what we can also note is that we have more extension, we have more periods of extension, and the basin is also deeper. We can also note that the slab morphology now looks very different. So instead of the standard anchoring period, we have a flattening behavior. And this is then followed by slab avalanching into the lower mantle at around 60 million years or so. And if we look at the trench retreat, we can observe that this is considerably larger than our homogeneous overriding plate, and also to the overriding plate where the continental keel was spatially restricted. So what if instead now we change the properties of the continental keel and we make it denser? And we can see that in this case, we still have this foreland area very well defined, But this time around, we can see that the basin, the foreland basin, is much narrower and is less steep than the two previous cases. We can also notice that the horsts or the shoulders of the basin are much steeper, much higher than the two previous cases. But if we look at the slab morphology, this is very similar to our homogeneous case, and our heterogeneous case where the keel was spatially limited. If we compare the trench retreat, we can see that the trench retreat for our homogeneous case is still the least trench retreat that we see, so this one in blue. However, the highest amount of trench retreat is once again observed for our homogeneous continent with the widest or the longest extent of continental keel. So if we had to compare all four models together, we can see here at top left is our homogeneous case, and on the right and bottom, we can see our heterogeneous cases. And we can see that heterogeneity allows for the formation to be constrained within a well-defined foreland region. And what we can also notice is that when we have more heterogeneity, or when heterogeneity is more pronounced, then we have more deformation and more extension. And what this means is that heterogeneity is allowing the partitioning of the plate speeds at our subduction zones to be focused in our foreland region. And this then therefore allows us to see this high amount of trench retreat in the model. So then what if we explore this partitioning a little bit more and we increase the trench retreat even further? What do we see? Well, what I'm showing you here is our model with the highest amounts of trench retreat and rollback that we have. And what you can see is that we do still have this foreland region, and we do still have the formation of this foreland basin, which is considerably deeper than the previous cases. And what we can see is that when we have this fast trench retreat, this allows for the spontaneous development of a flat slab morphology in the upper mantle. And this then in turn encourages this high amount of deformation, both within the foreland region, but also on the overall continental overriding plate. So in conclusion, we need to have a really well-resolved free surface if we want to understand how plate velocities are being partitioned in a subduction zone, and to what extent this affects the deformation in foreland. The second thing that I want to point out is, despite having very similar slab morphologies across all our models, the topography is very different, which means that we really need to understand both the properties of the continent, but also the subduction zone interface, because this clearly can influence both the plate motions, how these are being partitioned across our subduction zone, and this in turn can enhance the foreland deformation and may even affect flat slab formation.
Excellent. Thank you so much. As we did yesterday, we will leave the questions for the discussion session that we have later in order to stay on topic and on schedule. But I think this deserves a round of applause in the list, and we can move on to the next talk, which will be given by Emmanuel Njinju about tomography-based convection and melt generation beneath the Rungwe volcanic province in East Africa. Emmanuel, feel free to share your screen and unmute yourself and start your presentation.
Okay.
We can hear you.
Can you hear me now?
We can hear you. That's fine. We don't see your slides yet.
Can you hear me now?
We can hear you and we can see your screen.
Okay, that's good.
Excellent.
Yeah, thank you once more for inviting me for giving me this opportunity to share with you my, to give a short presentation about my research in aspect, which is focused on melt generation beneath the Rungwe volcanic province from tomographic-based convection. So to be consistent with this workshop, I will give a very short background and focus on the methodology and results. So first of all, the main motivation is that the eastern branch of the East African Reef System has numerous volcanic centers, as indicated with the red triangles and the presence of flood basalts, which suggests that the melt might be playing an important role in enabling rifting. However, the western branch of the East African Reef System is magma poor, has very sparse volcanic centers, including the Rungwe volcanic province, which is the southernmost volcanic center in the western branch of the East African Reef System. Given that the western branch is magma poor, there is therefore need to investigate deep melt generation to better understand the role that melt plays in rifting. So to better understand that role, there's need to even investigate if melt is actually present at depth before worry about how the melt will migrate through the lithosphere. So in that regard, I recently developed a model of lithospheric modulated convection that incorporates melt generation beneath the Rungwe volcanic province. And here we were able to generate melt beneath in the sublithospheric mantle beneath the Rungwe volcanic province. However, for very elevated mantle potential temperature, which suggests there must be a heat source at the base of the lithosphere beneath the Rungwe volcanic province, maybe from plume materials. And which means to better constrain melt generation will necessitate including upper mantle constraints, maybe from shear wave velocity tomography. So we hypothesize that decompression melt beneath the Rungwe volcanic province is generated from thermal anomalies due to plume materials. And in the shear wave tomographic studies by Emery et al. Suggests the presence of a low velocity zone that rises at depth and flows laterally at horizontal depth to focus beneath the Rungwe volcanic province. Such low velocity anomalies might be due to the presence of plume materials. However, there are still some fundamental scientific questions that remain unanswered, like is the melt actually at depth beneath the Rungwe volcanic province? And what is the source of the melt? So in order to address these scientific questions, we model a time-dependent tomographic-based convection using aspects in a 3D domain. And we actually solving for the velocity term in the Stokes law, which is a conservation of mass and conservation of momentum equation. And in the conservation of momentum equation, the shears or the viscous forces and the pressure gradient forces are balanced by the buoyancy forces, which is the main force driving mantle convection. And the main important thing to note here is that we are applying an elastic liquid approximation in our formulation, which is based on two assumptions. The first assumption is that the density variation relative to a reference density profile is small and can be accurately represented by Taylor expansion about the reference temperature and reference pressure. And the second assumption in the inelastic liquid approximation is that such density variations can be neglected in the mass conservation and mass and energy conservation equation and only considered in the buoyancy term. In that regard, the mass conservation equation, the density would simply reduce to simply the reference density in the mass conservation equation. And since we are interested in modeling melt generation, we also simulate temperature changes due to heat transfer in the model by solving for the temperature term in the energy conservation equation, the temperature term T in yellow. And we know in the energy conservation equation, the heat flow by advection and the heat flow by diffusion are balanced by the different heating models. And an elastic liquid approximation also checks that there should be shear heating and adiabatic heating. Those are the first two terms on the right-hand side in the heating model. But since we are modeling melt generation, we also include the latent heat of melting in the heating model. An important point to note in our model is how we constrain the initial temperature condition. We use the lithospheric structure beneath the Rungwe volcanic province, which is part of the lithospheric structure of Africa derived by Fishwick in 2010 from surface wave tomography. And the image you see here is a lithospheric thickness map. The hot colors represents regions with thin lithosphere, and we see the lithosphere's thickness beneath the Rungwe volcanic province with thickness of approximately 100 kilometers. And the lithosphere gets thicker as you go beneath the Malawi Rift, reaching up to 200 kilometers in some places. So we use this lithospheric thickness to constrain the initial temperature of the lithosphere. And an important point to note is we assume a conductive geotherm for the lithosphere with a linear gradient from the surface to the base of the lithosphere. The surface temperature is 298 Kelvin, and the temperature at the base of the lithosphere, we assume it to be an adiabatic boundary. And Mackenzie and Becker in 1988 suggest the adiabatic temperature gradient can be represented by the product of the thermal expansivity, the temperature, gravitational acceleration divided by the specific heat. And if the mantle potential temperature is the surface projection of an adiabat, then if we integrate the adiabatic gradient from the LAB, from the base of the lithosphere to the surface, then we can get the temperature at the LAB or the temperature at the base of the lithosphere in terms of the mantle potential temperature, where ZLAB is simply the depth of at the base of the lithosphere is simply the depth to the LAB. And then TP is the mantle potential temperature. And geochemical studies by Rooney suggest that the mantle potential temperature beneath the Rungwe volcanic province ranges between 1693 to 1723 Kelvin. And the temperature in the sublithospheric mantle will simply be, still in terms of the mantle potential temperature, will simply be obtained by replacing ZLAB with Z, where Z will be greater than ZLAB. So that will be the background temperature in the sublithospheric mantle. So if we replace ZLAB with Z, then we'll get the background temperature in the sublithospheric mantle. Now, the most important point in this study is how, and where the study actually gets its name, is how we constrain the excess temperature in the sublithospheric mantle, and using shear wave velocity perturbations from the Emery et al. Model. So the first figure you see here is a depth slide at 150 kilometers for the shear wave velocity perturbation derived by Emery et al. In 2019 from ambient noise in Africa. And we can see that we have low velocity zone focus beneath the Rungwe volcanic province, and if we convert this shear wave velocity perturbation first to an equivalent density perturbation by multiplying with a velocity to density conversion factor of 0.15, which Becker in 2006, also Ben and Conrad, Ben and Ligo Bertoloni in 2006 showed that we can use a conversion factor of 0.15. And then the next step is we convert the derived density perturbation to the equivalent temperature anomaly by simply multiplying by a negative the reciprocal of the thermal expansivity to get the excess temperature. So here is a depth slide along profile A prime, and we can see the excess temperature in D here, figure D here. And we see that the excess temperature goes as high as 250 Kelvin, and the maximum excess temperature is focused beneath the Rungwe volcanic province. So the next step is we add this excess temperature to the background temperature of the sublithospheric mantle to get the initial temperature structure, which is indicated here or shown here in 3D. And we also have a 1D depth profile beneath the Rungwe volcanic province here. So this 3D figure also shows our model geometry, and we can see our model extends up to depth of 660 kilometers. So the next important thing is mantle convection is also highly dependent on the rheology, but we are focused on melt generation in the sublithospheric mantle. So we want to avoid deforming the lithosphere. So we make the lithosphere rigid by giving or imposing a very high constant viscosity for the lithosphere. We give it a viscosity of 10 to 23 pascals second. But in the sublithospheric mantle, we implement composite rheology of dry ravine, and whereby the composite rheology is simply the harmonic average of the viscosity that we get for dislocation and diffusion, creep, flow law. And we use the composite viscosity as a background and viscosity, and also include porosity weakening to get the viscosity in the sublithospheric mantle. And the next important thing is how we implement partial melting in our model. We use the melting parameterization of peridotite after CAT in 2003, and we focus on modeling low degree melting of lessolite prior to the exhaustion of clinopyroxene. And the important thing here is the melt fraction is simply directly proportional to the temperature in excess of the solidus. So when the temperature of the geotherm exceeds the solidus, then we'll have melt generated. But when the temperature is less than the solidus, we have no melt is generated. And once the temperature exceeds the liquidus, which is a very rare case, then we have 100% melt. And in this melting parameterization, the solidus and liquidus have a quadratic relationship with pressure, as we can see here. And in a figure says a lot than the equation. So we can see in the figure here that melt will be generated if and only if the geotherm crosses the solidus, like we see the melting region, and the blue and green are simply geotherms for different mantle potential temperatures. So we tested a different range, like we tested potential temperatures of 1573 Kelvin to up to 1723 Kelvin. And the dashed line here is for a potential temperature of 1573 Kelvin, but we see that it won't cross the solidus. But once we add excess temperature that we derive from shear wave velocity perturbation, we see it crosses the solidus. And the green line here is when we use a very high mantle potential temperature, even without excess temperature, we see it crosses the solidus. And for the results, this is how the tomographic-based convection model looks like. And the background colors are vertical velocities, where the hot colors represents regions of upwelling, and the cold colors represent downwelling, while the arrow represents horizontal flows. So this is a depth slide at 250 kilometers there. We see upwelling focus beneath the Tanzanian craton, and it flows in a northwest southeast towards the Malawi Rift, and at a rate of approximately 3 centimeters per year, and tends to focus beneath the Rungwe volcanic province at shallower depth. The upwelling is focused at shallower depth and flowing at a slower speed of 1 centimeter per year. And the beneath the Rungwe volcanic province, the horizontal flow pattern seem to be have a radiating flow, which is characteristic of upwelling. And interestingly enough, this we could generate melt also that is focused beneath the Rungwe volcanic province with melt fraction generally less than 1.5%, and the melt is generated at a depth range of 130 to 150 kilometers. So we put all of this together to better interpret. So this figure here shows the top panel here shows our tomographic-based convection and melt generation. So I'm comparing the top panel, and the lower panel here is our melting model for lithospheric modulated convection without upper mantle constraint. So the important thing here is how we compare, or what improvement have we made in our model. We see once we include upper mantle constraints, like in the top panel, upper mantle constraints from shear wave velocity perturbation, we reveal some flow patterns that are not evident in the case we model the convection simply from lithospheric modulated convection. we can see upwelling happening beneath the Tanzanian craton, and we can see a corner flow here adjacent to the Bangwelu block that are not evident in the convection model that is simply driven by variation in lithospheric thickness. And then and what is common in bone models is that we have upwelling focus where the lithosphere is thinnest beneath the Rungwe volcanic province and generate melts at similar depth ranges. But for the tomography-based convection, this melt is generated for a lower potential mantle potential temperature than for the case of a lithospheric modulated convection with potential temperature of up to 1748 Kelvin. This shows that it's very important to include upper mantle constraint if we want to understand or better model mantle flow. And so we conclude this study by suggesting that actually plume materials might be present beneath the Rungwe volcanic province due to the high excess temperature that we derive of up to 250 Kelvin. And this is characteristic of plumes from petrological studies. Also, geochemical studies by Hilton et al. In 2011 suggest high helium isotopic ratios of up to 15 RA beneath the Rungwe volcanic province. And this plume material we have just shown from our study that can generate melt beneath the Rungwe volcanic province. And we have also shown a review from this study that upper mantle constraints are necessary to better simulate mantle convection. Thank you.
Excellent. Thank you. Please join me in thanking Emmanuel for this talk. And as I said, we will leave questions for later. In order to stay on schedule, we will move on to the next talk, which is given by Sascha Brune about fault network evolution in continental rifts, surface processes, and automated fault analysis. Sascha, great, you already share your slides. Feel free to start your presentation.
Okay, looks good. Can you hear me?
Yes, everything fine.
Excellent. It's great to see so many of you. It's really a nice meeting. So this talk is based on a big collaboration. And first of all, it's Derek Neuhardt's work, who has been coupling aspect and fastscape. He submitted his thesis in December and he's taking a well-deserved break, so he's not presenting himself. But also N and Xiaoping, Yuan and John Braun, who are from the fastscape side. And then for the fault analysis part, this is mostly Thilo's work, but we collaborate with John on this. And then there is Pauline, who did a bachelor internship, who also is feeding back into the models that I'm going to show. All right, so there's these two parts, fastscape and aspect, and then the fault extraction. Let's start with the fastscape part. So for those that are not familiar with that, that's a surface process code. And for us tectonics people or deep earth people, surface processes is just a way to erode and to redeposit stuff somewhere. For the surface process people, there's so much more in it. So it's important to say what kind of processes are actually covered by the codes. I put the formula up here. This is what the heart of fastscape. And what it's doing, it's computing a change in topography by having a tectonic uplift force. This is what the geomorphologists see as a driver of topography. So this is coming from below. And then there are two processes in there. One is the stream power law that is driving incision, and then there is a hill slope diffusion. And the actual processes in there are really small scale. It has to do with weathering and with how much rain is falling, how the rain is distributed through the network. And these two equations are really the absolute extremely simplified version of how you can treat surface processes. So what incision is doing, it's looking at the local slope, and it's looking at the size of the upstream drainage area. And then it has an erodibility coefficient. And how you can think of this is just you have a big river where you're standing at a place, you have a river. The slope is defining how fast the water is flowing, and the upstream drainage area is defining how large the river is. And then KF is a factor that's defining how easy the material can be eroded that you're standing on, or how much rain is falling upstream. So this is a little fudge factor that is condensing a lot of different parameters. And then hill slope diffusion is just a diffusion equation where you have the high gradients diffusing away with a diffusion constant that you can set. So this is surface processes, and then Fastscape is implementing this in an open source way. So that's something very nice also for reproducibility and for reusability, that we can couple two open source codes to each other. Then of course it's fast. Yeah, it's called Fastscape, and this is of course nice that it's fast, but it also has its caveats. So Jean always says every routine that he implements has to be order n and implicit, so it has to be as fast as possible, and this sets some limits to other things. So it's not only good, it makes things fast, but it makes things in some places also less accurate when it comes to advection, for instance, or when it comes to processes that are not easily treated in this fast way. Okay, and then on the continent, we have incision and diffusion. These are these two parameters. And in the marine part, we have diffusion, and we have homogeneous sedimentation. So you can see this as background sedimentation rate. So these are our surface processes. Here are some references, and you can look up on these websites what's actually going on. So Derek is the one who implemented all the work and heavily supported by Anne. And so we combine aspect rift models. This is what we've been focusing mostly with this Fastscape Fortran library. There's a good, interesting comparison to be made. So first of all, we look at faulting from 500 meter to kilometer scale, and Fastscape has processes that live on 100 meter to kilometer scale. So that's the same size. And that's, in fact, the reason why it's useful to couple surface processes to tectonics, because they act on similar lateral length scales. The model size is also can be very similar. So we can treat the entire models and couple entire models together. Time steps are quite different because the tectonic time steps usually are much larger than the surface process evolution time steps. So there's something that one has to think of. Aspect is of course parallelized. Fastscape, because it's so fast, it's no need to parallelize it, which can raise some problems. Aspect can have mesh refinement at the surface, and Fastscape lives on a regular grid, so there has to be some interpolation to be done. Aspect can be 2D in a vertical plane, and we have Fastscape on top as a 2D horizontal plane, where we let the two planes communicate in one or another way. Or Aspect can be 3D, and then Fastscape is just the 2D surface of that. So these are the options that are out there. How both are coupled is through a big aspect loop. Let's say this blue arrow is the big aspect loop. We have a new time step. We compute the surface velocities. And these surface velocities are the U in the Fastscape equation. These are the tectonic driving forces that Fastscape is using as input. Then Fastscape is doing its job. It's making several time steps. It's equilibrating the surface, eroding onshore, sedimenting offshore. So it's changing the surface. And this changed surface is then put back into aspect by changing the mesh velocity. We just move the mesh according to the new surface that Fastscape has been computing. And if we create, if we have to add new material to account for this new mesh, so if we are in an offshore domain where we sediment, then we can use the boundary composition model to fill sediments into this hole that we generate, or anything else, whatever you want. So this is how it works. And what's important is that there, in the time stepping scheme, we initialize Fastscape only once. That's important because the high resolution topography of Fastscape, we want to keep that for all time steps, and we don't want to lose it by interpolating back to aspect. This is how we started off, and where we realized that this is a lot of information that's lost. So we initialize Fastscape once, and then we update Fastscape all the time. So during the cycle, Fastscape is always keeping its old topography in a memory, and then this topography is updated in next time steps. I'm trying to focus really on the essence here. So there are many more details that one can discuss, but this is the input parameter section that we have been using for the study that I'm going to show in a minute. So we have a subsection on mesh deformation where we update these meshes as I outlined before. We have a subsection on Fastscape itself that is setting several parameters that are key to Fastscape. boundary conditions, erosional parameters, marine parameters. That's it. Over the last years, there were several problems that we managed to solve. So this coupling across these mesh refinements, restarts, one has to write restart Fastscape files to adequately restart, periodic boundary conditions, that was also quite a challenge. But there are also some remaining problems. One big thing that you always have to keep in mind is that many surface process codes are not mass conservative, which is something that, well, it's not really intuitive, but it's there, and this problem is still out there. And so far, we only tackled Cartesian geometry, so there are no non-Cartesian geometries covered by this. Okay, so we know that if you have Fastscape surface processes, you can create beautiful animations. I focus really only in the next slides on some outputs. I don't want to go too much into the science part because there's not much time. So this is a rift model where we pull at the sides. We have erosion onshore, deposition offshore, and we track the sediments and we track the age of the sediments so that we can see how well sediments are tilted, how the basins are filled, and how the rift system as itself evolves. We get some islands eventually that are drowned again. We get progradation of these rivers. So many interesting processes that we can look into in detail. Oh, right, and I forgot to mention, so this is Derek's paper. It's on review and tectonics, and it's available at Earth Archive. If you want to Google it, here's the name. It also comes up later. And this is a preliminary study where we put the tectonic system into compression. So we have been pushing from the sides, and we have been eroding in an asymmetric way. We have been eroding more on the right side than on the left side. And so we create a symmetry. And that's something that is visible in the Northwest Argentine Andes, where we have wind from the right side. And so we erode more on the right side. And this wind direction that is shown here on the right, and that is affecting the Fastscape erodibility through orographic control, is then affecting what the tectonics are doing, because we take more surface away here. We erode more heavily on the right-hand side. On the western side, we essentially motivate aspect or the tectonic model to have higher uplift rates on the right side. And so there's an asymmetry that is integrated in there. And then on even larger scale, so this is the model that Mikhail Pons has been running, and he's also here with Stefan Sobolev and also with Derek. So a subduction model similar to what you've seen in Antoniette's talk, only that now here he played around with Fastscape, and he gets some episodic orographic phases and extension phases that are really well imaged with Fastscape as well. Okay, you can ask Mikhail if you have more questions on this. I move on to the second part, fault extraction. And this is slightly linked to the first part, but first I come to the technical details, or a bit the motivation. So we are used to get petrological results in models, in numerical models, PTT parts, and how the minerals are evolving. But this is an attempt to also extract structural geology from geodynamic models. But it's work in progress, so this has to be taken with a grain of salt. One of the questions that we have been addressing is displacement length paths. So displacement along faults is the vertical displacement, and the length is just the length of the fault. And these displacement length paths are visible in these displacement length diagrams. So this is about how faults accrue their length and their displacement. And some people think they just move along a horizontal until they die. Others say they grow first in length and then they accrue displacement and then they die. But for all of them, they die in the upper right corner if they're really long and have a lot of displacement. This is one of John's beautiful models, and this is a continuum model. So how can we get faults out of continuum models? Faults are 2D interfaces, and how can we quantify fault parameters like dip, displacement, length, and how do we track them through time? So this is the challenge. And what we do is, of course, we extract faults from models and quantify their characteristics. And Thilo has implemented a fantastic Python library or Python workspace that is using image analysis and all kinds of database approaches to do exactly this. It's also open source. He put it on GitHub. As I said, it's work in progress, but you are welcome to try it out. And what we are doing is we follow this recipe. We have 5 steps. First, we take our topography, our strain rate at the surface here, just from a model like John's. We take the strain rate, we threshold it, we say we are only interested in the center of the faults. So we skeletonize it, which is essentially projecting them on one-dimensional lines here. And then we group those lines in a way that we can call them fault network. And this grouping is following a certain strategy where we have edges and nodes, and these edges are connected as a network of components to faults. And then finally, we have to track faults through time, so to make to follow them up and see their evolution. And then we can also extract properties like dip, like extension, throw, kinematics, orientation. Okay, so this is now Derek's model that you've seen before, only that we extract all the faults that are forming these basins. And for fun, we just show whether the fault is dipping to the left or dipping to the right here, but we can also extract other properties. So this is just to illustrate that the workflow works in 2 dimensions. And we can also discriminate between black faults that are dead faults that are not deforming anymore, and then the colored faults that are currently active. So there's something interesting that one can get out of here. And for that, I recommend to look at this paper that is at Earth Archive now. But of course, we can also do 3D models, and this is my favorite bit. So I have a 3D model where the mesh is refining towards the center. It's a model where aspect is coupled to fastscape. And if we look at the evolution, then we get nice rift shoulder uplift. We get basin ward localization of the faults. We get some little fans here from surface processes. And we can see how all this is interacting with each other. And we can do this by extracting the faults and looking at higher level structural output, not only at the images. And this is what's at the core of this endeavor. But first of all, I show a map view of the same model. And here we show slip rate on the faults. So this is really a fault parameter. This is nothing that you can get out of continuum models, because slip rate is just defined only on the fault. And you see how the distribution of slip rate along the fault is low at the tips and it's high at the centers, and how it's evolving through time. And there are 2 take-home messages from this exercise. One is that we have coalescence of faults, that many faults in the beginning compete with each other and form these survivors. And with the survivors, they have high strain rate at the center, high slip rate. And this high slip rate domains, they enlarge, they accrue their length while they get their displacement. So that's something that we would see in this displacement length plots as high length at first and then a lot of displacement afterwards. And we can also see how faults die. And this is one example. This big fault is disintegrating. It's not just stopping and ending up with high displacement, high length in the upper right corner. Instead, it's disintegrating and getting smaller length and high displacement. So faults don't die in the upper right corner of this diagram. They die in the upper left corner of this diagram. This toolbox is very versatile. And this is what I want to underline here. We also use it to extract faults from topographic data, and this is what Pauline was doing. Or Thilo has been extracting faults from seismic active seismic data. And so I think if some of you are interested, one can adopt these techniques and one can apply it to other things, not just faults. So just to illustrate this, I stole 2 images from the 1-slide summary from yesterday's run from Aaron. I was thinking that these plate boundaries here, they can be treated in the same formalism that we used for the faults. And you could get plate kinematics from these models for the plate boundaries, how their velocity evolves through time, their obliquity, their geometric properties. Or I took this one from Urushi. You could map out your plate boundary kinematics and geometries in the same way. Only if you're interested, of course. But I see quite a big potential for this kind of post-processing. Okay, with that, I come to the conclusions. So we successfully coupled aspect and farscape. And when I say we, I mean Derek mostly. It's 2D and 3D Cartesian, and there's an active pull request to bring it back into mainline. And this is actively worked on right now, but as I said, Derek is taking a well-deserved break. Then we have this fault extraction that is a Python-based post-processing that is looking at geometries and kinematics, and it can track features through time. And here's again the link if you would like to take a look at it. And before I finish, Claudio Faccenna, who is now at GFZ, asked me to advertise for this postdoc position. So he wants a numerical modeler to look at active plate margins, feedback and interaction of surface processes, and develop models and compare to analog models and numerical models. And if one of you are interested, well, you have to be quick. Deadline is 30th of January. But I think it would be a great environment, and bringing aspect also to other sections would, of course, be great. Okay, thanks for your attention.
Excellent, Sascha. Thank you so much. I think we all agree. Those are some amazing animations that you're showing, and the coupling to service evolution codes looks like a really promising future approach, as well as the post-processing using image processing. This concludes our first session with short presentations today. We will have a second one, but first we will take a break. And after the second session of short presentations, we will cover all of the questions that you might have about the short presentations. So keep your questions or write them down so that you don't forget them. And we will come back to that. And we will meet again here in about 20 minutes. But first, please thank all of the speakers of this session again. And we will see all of you in about 20 minutes at the top of the hour. Thank you.